Jason Lowe from California State University, Northridge. Right, so if I say to you, let's go to the movies or let's go to a football game, then you have some idea of what I mean by those phrases. I mean, the meanings of these phrases are different from person to person slightly, but then there is a common meaning when we use these phrases that's consistent for everyone. And so that's why they are part of our everyday vocabulary. And so the motivation for our project is we want to, and we probably learn what these phrases mean by maybe going through the motion multiple times, or maybe by observing other people going through these experiences and using our inductive reasoning to form an abstract concept of what these things mean. So in this project, we are trying to give machines the ability to do the same thing. And the mathematical language that we want to use, that we're using, is the language of wiring diagrams. A wiring diagram is just a graph, so it has arrows and vertices, but every vertex is labeled with a sensor reading. And by sensor, we mean something that can be very broad. So it could be a simple sensor measuring temperature, or it could be a complicated piece of software analyzing online activity to see whether a certain behavior has occurred. So the wiring diagram on the left, for example, represents the idea of a person buying biscuits. And if you imagine writing a piece of code, detecting whether that event has occurred, you can incorporate that into a more complicated wiring diagram. So there's this compositionality in the theory of wiring diagrams. And right, so we have written some algorithms to try to extract wiring diagrams from data. And for us, as long as the data comes in the form of sequences, you can put it into our algorithms. So it doesn't matter what types of data the sequences originally come from. So here's an example where you have 3 sequences, and say you're trying to extract the common theme, the common meaning of these sequences. You can use inductive reasoning that's incorporated into our algorithms. So depending on what level of abstraction or generalization you want, you can get different wiring diagrams that represent the common themes. And so we realized that it's not easy to get data related to human. So we decided to generate our own data. Or rather, my student wrote a computer game. So we trained a computer agent to try to play and win this game. So in this game, so there are certain items that you have to collect, and you have to use them in appropriate ways in order to win the game. So for example, you have to collect a key at some point to open a door, but there's a rock blocking the door, so you have to destroy the rock first somehow. And so we trained the computer agent. We recorded all the moves of the agent, so that data was turned into sequences for us to use. And here, this picture on the right is like a heat map that was generated by our algorithm. And our algorithm was doing some sort of clustering, which we call Hasse clustering. So the last slide. So we focused on the cases, the episodes where the computer agent won the game. There were about 100 sequences, and we put those sequences into our algorithm, and the output in the second version of the game, the output was these 2 wiring diagrams on the right. So the point here is that these graphs are readable and understandable to humans. They are graphs, but they have labels that you can try to understand using the key on the left. And if you try to, so that the 100 sequences that we had were all common to the agent winning the game. And if you actually sit down and understand the 2 wiring diagrams on the right, they represent exactly the 2 unique winning strategies of the game. So we converted data into wiring diagrams that are understandable to humans. So right now we are looking for other contexts or scenarios where we can apply our algorithms. And we are also trying to develop the mathematics of wiring diagrams more in order to overcome the constraint that comes from combinatorial complexity in our mathematics. That's all. Thank you.
Thank you so much, Jason.